When we solve this equation, what we find is a solution for x is a function of t, that basically has two parts. There's the first part, a cos omega t minus delta, and I'll come back to this in just a second. Then plus, there's another term over here that damps out exponentially. This term is basically dependent on where in the motion do we actually start our forcing function, what's the phase difference between the motion of the oscillator and the forcing function. Those are the initial conditions, and whatever they are, they damp out, kind of like the motion of the unforced function damps out exponentially. So over time, whatever this is, it's going to go to zero. It's going to damp out. So we'll just ignore that part. This part is the steady state part. All we've got is an amplitude and a cos omega t time dependence here. So we've got something that basically is going to keep oscillating indefinitely. There's a phase difference here, some phase difference. What is this? Well, cos omega t, that is the phase of the forcing function. The delta then tells us what's the difference in phase between the solution and the forcing function. Imagine this is the force, and I push and then I pull. Push, pull, push, pull, so to speak. Imagine with a child on a swing, imagine you could actually push the child, but then pull the child back, and then push the child and pull the child back. So you've got a positive force and then a negative force. So imagine this is the force and this is the displacement. So here we've got pushing, pulling, pushing, pulling. Now delta tells us the difference in phase between the response and the force. So if this is the response, are they like this? In phase, like this? Are they 90 degrees out? Are they 180 degrees out of phase? So it's like this. Are they 90 degrees out of phase? So it's like this. This is not easy to do, by the way. You should try this. Is this lagging behind this one? Or is it leading this one? Like this? So what's the phase difference? We'll take a look at that. We'll come back to that in a second. But the amplitude of the motion has this relatively complicated form. We've got the size of the force. Well, that makes sense. The bigger the force, the bigger the response we would expect. Pushing the child, the more you push, you would expect the bigger the response of the swing. But it also depends on this complicated denominator. And what I want us to look at is this part right here. Remember, the smaller the denominator, the bigger the overall value of the fraction. So if we decrease this, now how could we decrease this? If omega gets close to omega naught, imagine omega starts out very, very small, and we are increasing omega. When this is small, we'll have, well, this will be small. We'll basically have something that looks like m squared omega naught to the fourth. But as omega increases, this term will get smaller. The overall, even though this term will be getting bigger, the overall denominator will still be getting smaller because of the reduction in this term here, and the amplitude will be getting bigger. And it will continue to get bigger until omega is equal to omega naught, in which case this term will be 0, and that will be the minimum value for the denominator. And then as omega starts getting even larger than omega naught, this is going to start increasing again. This is still increasing. So the denominator gets bigger and the amplitude gets smaller. So as omega increases from 0 to omega naught to larger than omega naught, the amplitude is going to go from some small value to a larger value and then back to a smaller value, maximizing where omega equals omega naught. Let's graph that and take a look at what that means. The shape of the curve will also depend on the value over here involved with B and mass, so let's see what that's going to look like. If we look at the average power absorbed by the oscillator, what happens is when omega, this is a plot of omega versus the power, when omega is small, the oscillator absorbs a small amount of power, a small amount of energy per time. But as omega increases, more power goes into the oscillator, maximizing at omega naught, and then decreasing as omega continues to increase. So what's going on here? Well, the oscillator is going to keep absorbing power from the forcing function until it's losing as much energy as it gains. It's going to lose that energy to the friction. So it will keep absorbing energy, increasing its motion. These are part of the transitory parts that damp out eventually. Increasing its motion until it's oscillating so much that it's taking in as much energy from the force as it's losing to the frictional force, in which case it comes to a steady state solution, and that's when it's just going to maintain a constant amplitude oscillating. But what happens is this peaks at a frequency of omega naught. Now this is very, very interesting. What is going on here? Let's remember what's happening. This is the frequency of the forcing function, omega naught. That's the frequency that you can think of it as the frequency that you're pushing on the child. When that matches omega naught, now what's omega naught? Omega naught was the frequency at which the oscillator would oscillate naturally, so to speak, with no friction. Now, how does this work? What's going on here? What does this mean? Well, let's take a look at the physical example that we had before. So here I've got a mass on a spring. And let's imagine that I'm going to apply a forcing function. And to do this, I'm going to move my right hand up and down a little bit. If I do this very slowly, in other words, with a small omega, nothing much happens. The mass doesn't do much. Okay, it moves up and down a little bit, but not a whole lot. Now, if I do this very rapidly, well, something is going to happen a little oddly, and that is that the spring is going to start to oscillate. But what I want to do is watch the mass. So if I do this fast, the spring starts oscillating, but the mass is really still not doing that much. Okay, it's not oscillating a whole lot. But now I'm going to start applying a forcing function at the same frequency as the natural frequency of the spring. Well, what's the natural frequency of the spring? Well, let's experimentally determine that. So I'll start it oscillating, and let's just think 1, 2, 3, 4. So I'm going to start moving my hand at that frequency. 1, 2, 3, 4. 1, 2, 3. So much energy gets absorbed by the spring that eventually the oscillator falls apart in this case. Well, if you had a spring that was a little better suited for this sort of thing, what would happen is that would just oscillate more and more and more until finally it was losing as much energy from friction as was being absorbed from the forcing function. You can think about this still when you are pushing a child on a swing. Ask yourself, how would you push a child on a swing? Would you push them like this? At a very high frequency? No, obviously the child's not going to like that at all. So no, that's not going to work. And remember, what's the point? To get the biggest response of the system. In other words, in this case, for the child to get the biggest swing. Do you push very slowly at a slow frequency, pushing this way, and then pushing back this way very slowly? Is that going to give the child a big swing? No. Also, how do you push the child? You push the child, and then when they come back, you push them again. When they come back, you push them again. In other words, you match the frequency of your pushing to the frequency of their swinging. You match your frequency, the frequency of your forcing function, to the frequency, the natural frequency of the system, the child swinging. You match omega naught to omega, you match omega to omega naught, and that's what's going to give the child the largest swing. In other words, the biggest amplitude for the motion, where the most amount of power is absorbed by the system. Very good. Well, okay, that makes sense. That makes a lot of sense. The shape of this depends on the quality factor that we talked about before. A different quality factor might give us a response that looks like this. Maybe not nearly so peaked. If we look at the width of these curves, I tried to draw this so that this was wider than this one. The Might be better to actually draw this. Let me redraw this just a little bit to make this look a little more obviously. Okay, something like that, so that the width of this we can see is obviously less than the width of this. The more narrow the response, the more power we get into the system, and this is what we have with small damping in other words, a high Q value. This one then is more damping with a low Q value. Okay, very, very good. And in terms of the response in omega, we have that the quality factor, same quality factor we talked about before, is equal to the ratio of the resonant frequency to the width, delta omega, of the curve. So that's another way of thinking about the quality factor. Now let's take a look at that phase difference. Remember, we had a forcing function that was f omega t, f was cos omega t, while the response we had was x was equal to cos omega t minus delta. So we had that phase difference between the force and the response. Let's take a look at that delta just for a second. So remember, our solution for delta was tan delta was equal to b omega over m omega naught squared minus omega squared. Let's look at this in three different extremes, so to speak. Let's look at this when omega is much, much less than omega naught. In other words, we're applying a forcing function that's very, very slow compared to the resonant frequency. When omega is much larger than omega naught, in other words, we're applying a forcing function that's much faster than the resonant frequency. And then when omega is equal to omega naught, in other words, the forcing function is just equal to the resonant frequency, like pushing the child on a swing just at the frequency that they swing back and forth. So what do we get? What happens to delta? Well, when omega is much, much less than omega naught, so imagine omega is basically very, very small, we get omega squared here minus a small number, so it's basically m omega naught. But the numerator, which has got omega, is going to get smaller and smaller, so the value here is going to approach 0. As omega gets smaller and smaller, this goes to 0. Tan of delta equals 0. Delta is the inverse tan of 0, or delta equals 0. So in this case, delta equals 0. I'll come back to each of these in just a second, and we'll take a look at physically what this would look like. When omega equals omega naught, so when omega equals omega naught, this term goes to 0, and we end up with tan delta going to infinity. As this argument goes to infinity, what's tan of delta? What's delta? Well, it's pi over 2. So delta is pi over 2. Okay? Now, what about when omega is much, much larger than omega naught? Well, in this case, omega squared is going to be much larger than omega naught. We get a negative quantity down here. We've got omega over a negative omega squared down here. One of the omegas cancel. We get negative b over m omega. Negative b over m omega. As omega continues to increase, that's going to go to 0. But it's going to go to 0 from the negative side, so to speak. So this is going to be a negative quantity approaching 0. Well, if you take the inverse tan of 0, you will just get 0 again. But we've got to think of delta as increasing smoothly. It's gone up to pi over 2. What it's going to do is continue to increase, because another angle that will give us essentially an infinite solution would be pi, when delta equals pi. So what happens is, as omega smoothly goes from a small value through omega naught and continues up to a large value, delta will actually increase smoothly from 0 to pi over 2, and then to pi. There we go. So physically, what do these look like? Well, let's go back to our motions here. So here's F, here's the response. So at a very, very slow frequency, the phase difference is 0. So as F goes up, the displacement goes up. As F goes down, the displacement goes down. And we saw that with the mass, that when I was moving it very slowly, when I moved the spring up, the mass went up. When I moved the spring down, the mass went down. There was no phase difference. F up, X up. F down, X down. As we hit the resonant frequency, we get a phase difference of pi over 2. And remember, the pi over 2 is in the solution for x, where x was equal to omega t minus pi over 2. So that tells us what the lag is between the position and the force. The position is lagging behind the force. So what does that mean? If the force is up, the position is on its way up. So we end up with a lag behind the position and the displacement, like this. So remember, this is the force leading the displacement. This is the displacement. So the displacement is lagging behind, like that. Okay? Pi over 2. But as we continue to increase omega, the phase difference goes to pi. So what happens in that case? Well, in that case, we get these basically opposite sort of situations where the force is up, the position is down. When the force is down, the position is up. And they basically go back and forth when the frequency is very, very high. Wow, okay, very, very good. That is a lot about oscillations. What we're going to do next time is use some of these ideas and take a look at another type of very, very important oscillatory behavior, and that is when we have a medium that the oscillations can move through. And that is the topic of waves, traveling waves, standing waves, all sorts of different wave phenomena. I'll see you next time.